Hey guys, welcome back to Crazy Chapter 2. Today we are going to start laying the foundation for how the quantum mechanic model applies to chemistry and why and how it's important to us as general chemists, as first year chemistry students. So just to get you guys caught up on where we left off, we had talked about this idea that classical Newtonian physics does not work for electrons. So classical Newtonian physics, we could say a baseball is going to travel from point A to point B, and it's going to do so along this line. For electrons, we don't have that luxury. So if we're talking about an electron moving from point A to point B, we are likely that it will probably most likely be somewhere in here that we would find that electron while it's moving. But we don't know for sure. Okay? So we have these probability maps. Schrodinger equation. So first and foremost, we are not going to touch this equation. That's a really complicated equation you can get to in third or fourth year chemistry, but we won't touch the equation. But the Schrodinger equation. So the Schrodinger equation is a wave equation. So that tells me that the solutions to this equation are waves. So where have you seen a wave as a solution before? Well, if you've taken trigonometry, you've got things like sine waves, cosine waves, things like that. So we have seen before where a wave can be an answer to a math problem. The difference between trigonometry and the Schrodinger equation is that his waves were three-dimensional waves. So the waves to his Schrodinger equation are three-dimensional pictures or three-dimensional maps. So these three-dimensional pictures are the probability maps. So what the solutions to the Schrodinger equation show us are the houses that electrons live in around the nucleus. So solutions to the Schrodinger equation are probability maps or probability distributions. This is actually a three-dimensional sphere. And what this shows us is the likelihood that an electron is right here in the middle is a much higher probability or likelihood than it would be out here around the edges. But we know with pretty good certainty, if I were to look for an electron, it would be somewhere inside of this sphere. So they would be somewhere inside of this house. So that's what the Schrodinger equation tells us. So what we're going to look at now are these three-dimensional waves, are these three-dimensional probability maps where we're likely to find an electron. So we're going to talk about what these houses look like, and then we're going to come back and talk about the electrons living in them. So here's a website that I found that gives us some really good pictures as to what these atomic orbitals look like. So let me go ahead and click into this website, and we will look at these. Make this bigger so you can see it. Okay. So the first solution to the Schrodinger equation gives us an orbital. So an orbital is just another name for the house that electrons live in. So the first solution to the Schrodinger equation gives us what's called an s orbital. So what we see here is that an s orbital is a spherical shape. So the solution to the Schrodinger equation gives us a sphere, and somewhere inside of that sphere is where we're likely to find electrons. So that's the first shape that we see. The second solution to the Schrodinger equation is going to be what's called a p orbital. So a p orbital has two lobes, so one going here to the right, one going to the left. So a p orbital has two lobes. Because of those two lobes, there's three different ways that we can orient this in space. So three different ways that we can move those two lobes. So we have three housing options. So here's the first one, left and right. Here's the second one. It's coming out at us, going back into the page. And here's the third one. It's going up and down. So three solutions to the Schrodinger equation. All of them are p orbitals, We just have 3 different ways to orient them in space. And when we stack these 3 p orbitals, one on top of another, one of the things that you'll notice is when we stack them all on top of each other, it roughly looks like a sphere. So this is very often why atoms are depicted as spheres, because when we start to put these orbitals on top of each other, that's essentially what they create. Okay, so S is sphere, P is double lobed, 3 different options. The next orbital we're going to look at is a d orbital. So a d orbital consists of 4 lobes. So 1, 2, and then 2 in the back here, 3, 4. So 4 different lobes for a d orbital. And the big take home here is there is 5 different ways to orient this in space. So 5 different ways we can orient a d orbital in space. So this one doesn't look like 4 lobes. It kind of looks like a donut. But just rest assured that there are, in fact, 4 lobes in this picture. So S orbital, sphere, only one way to orient a sphere in space. P orbital, the 2 lobes, 3 different ways to orient that in space. And a d orbital is 4 lobes, and there's 5 ways to orient that in space. That 1, that 3, that 5 are going to come back. And the last orbital we're going to look at is an F orbital. So this is the last one that has an application for us. For an F orbital, we've got 8 lobes. So we got 4 up here at the top, 4 down here at the bottom. But again, the big take home is the different ways that we can orient this in space, the different housing options that we have. So for an F, we've got 1, 2, 3, 4, 5, 6, and 7. So F orbital, 7 different ways to orient that in space. Okay. So the next thing I want to talk about is what happens as we start getting further and further away from the nucleus. So basic shapes of orbitals: S is sphere, P is double lobed, D 4 lobes, F is... What we see here is, first I want to draw your attention to the top. So in this top picture, I see a series of s orbitals. And these are kind of chopped in half so you can see the center of it. So these s orbitals are still spheres. But what I want you to notice here is that in the first s orbital, it's a very small sphere. And then when we go to what's called the second energy level, or we start adding more electrons, and this will come full circle in just a minute, that sphere gets bigger. And when we go up another energy level, that sphere gets bigger. So S's are always spheres, and they get bigger as we increase energy. P's are always double lobed. And there's always 3 options, and they also get bigger as we move up in energy. Same thing with D, same thing with F. So maintain their shape, maintain their orientations. They just get bigger and bigger and bigger as we move further and further away from the nucleus. Here's another website. I couldn't get this one to work on my computer. I love this website. I just couldn't get it to work at home, so I had to use other things. All right, so we have these orbitals. We have these housing options. We know that we will find electrons in those orbitals or electrons in those houses. The next thing we're going to talk about is something called quantum numbers. So quantum numbers are going to be the zip code to where we find these electrons. So zip codes. How does a standard zip code work? So standard zip codes are 5 or 6 digit numbers that tell you exactly where it is that you are living. So for example, zip code for here in North Carolina, the zip code's always going to start with a 27 or a 28. So that 5-digit code, 28, automatically puts us into North Carolina. I'm originally from Illinois, so my zip code growing up always started with 62, and that put me into the state of Illinois. So first 2 numbers give us a little bit of information about where we are in the United States. The last 3 digits are going to put us into a specific region, a specific county, a specific city, and then even if the city's big enough, a certain part of that city. So the last 3 digits are going to give us even more detailed information. So for example, if you were at the downtown campus, your zip code would be 28, you're in the state of North Carolina, 401. So that 401 puts you in eastern North Carolina, in New Hanover County, and then a specific portion of New Hanover County, or specifically in Wilmington. If you live in Leland, your zip code is 28451. So again, the 4 is putting us into eastern North Carolina. 51 is putting us into Brunswick County and then the town of Leland. So that's how standard zip codes work. Each number gets us a little bit clearer picture of exactly where that address is. Quantum numbers have a 4-digit zip code. So each solution to the Schrodinger equation can be identified or addressed by a unique combination of 4 integers. Each one of these integers is going to have its individual slide, so we'll talk more about each of them. But principal quantum number, angular momentum quantum number, magnetic quantum number, and spin magnetic quantum number. And what a zip code looks like for a particular electron is its address would look something like this. So maybe 2, 1, 0, +1/2. Okay. So by the end of this lecture, that address will have a meaning. You'll know exactly where that electron is residing. So the first quantum number is the principal quantum number. The principal quantum number is denoted by the letter N, so N equals, and it characterizes the energy. So it can have any values, a positive whole number. So N equals 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way up. For us, we're really going to deal with 1 through 8, 7 or 8. Okay. So it characterizes the energy. The other big take home is it determines the size of the orbital. So as I showed you on that one slide, as we increase the energy, as we get further away from the nucleus, the orbitals start to get bigger and bigger and bigger. So there's going to be 2 kind of take homes, 2 things to really remember about quantum numbers. The first one is, well, what does it tell us about the house? So the principal quantum number tells us size and energy. And then the other thing you're going to need to remember is, what are the possible values? So the possible values are whole number integers, 1, 2, 3, or 4. The next quantum number is the angular momentum quantum number, and this is denoted with the letter L, so that's a cursive L up there at the top. The angular momentum quantum number defines the shape of the orbital. So back to the sphere or the double lobes or the 4 lobes. Angular momentum quantum number tells us the shape of the house that we're in. So here are those just different shapes that we looked at. The possible values for the angular momentum quantum number are going to be a range from 0 to n minus 1. Okay, that's easy enough. What's n? So we can find n minus 1. Well, n is just whatever energy level we're dealing with. So let's just arbitrarily say that we're in the second energy level. Or n equals, n equals 2. So what are the possible values for this angular momentum quantum number? The possible values are a range. That word gets missed very often. So it's a range from 0 to n minus 1. In this case, n is 2. So it's a range from 0 to 1. 2 minus 1 is 1. So the possible values are 0 and 1. Okay. Let's look at another example. Let's arbitrarily say that we're in the 5th energy level. So n equals 5. So what would the possible values be for the angular momentum quantum number? Well, again, it's a range from 0 to n minus 1. So in this case, 0 to 4. So the possible values are 0 or 1 or 2 or 3 or 4. Those are all the possible values that we could have. Okay. So angular momentum quantum number. So angular momentum quantum number defines the shape of the orbital. The possible values are a range from 0 to n minus 1. But think back to some of the stuff that we've looked at. I didn't say that this sphere was a number or this double lobe was a number. What did I call those? Yeah, I call them S and P and D. So there's one just kind of little extra added thing to look at here. So when L equals 0, we are describing or talking about an S orbital. It's a sphere. When L equals 1, we are describing a P orbital, so one of the double lobes. When L equals 2, we're talking about a D orbital, and when L equals 3, we're talking about F. The magnetic quantum number. So this is our third quantum number here. The magnetic quantum number defines the orientation in space. So can we orient it in more than one way? If so, well, how many ways can we align that? The possible values for the magnetic quantum number range from positive L to negative L. So once you've defined the shape of your orbital, once you define what L is, then we can talk about the orientation in space. Okay? So let's just look at an example. So let's say that L equals 2. 2. We'll go 2. That's fine. L equals 2. Well, let's click back and look. If L equals 2, what shape is that? That's a D orbital. Okay. So if L equals 2, the magnetic quantum number, which is just M sub L, that's how we denote it. The magnetic quantum number can be a range, again, a range from positive L to negative L. So it can be positive 2 or positive 1 or 0 or negative 1 or negative 2. So there's our range. Okay. So remember when I said that 1, 3, 5, 7 was going to come back? Here it's back. Okay. What Well, let me say it this way. How many possible values do we have for the magnetic quantum number? How many options do we have to orient that in space? We have 1, 2, 3, 4, 5 options to orient that in space. 5 housing options. And when we looked at our pictures, how many different d orbitals was there? 1, 2, 3, 4, 5. Not a coincidence, right? So 5 different ways to orient that in space, 5 different options for the value, and 5 different d orbital pictures that we see here. Okay. So orientation in space ranges from negative L to positive L. And of course, you're going to need to know what L is in order to define this. All right, so the last quantum number is the spin magnetic quantum number. So the spin magnetic quantum number tells us the spin, the spin orientation of the electron. Okay. If we're using the analogy of these orbitals being houses, we can think of each house as a duplex. So in each orbital, 2 electrons can live. We can have up to 2 electrons in each orbital. So each orbital is a duplex. So what the spin magnetic quantum number tells us is who lives on the top floor and who lives on the bottom floor. In the next chapter, we're going to look at something called an orbital diagram. But what we'll see is, let's say this is our orbital. And we'll see that 1 electron lives on the top floor and 1 electron lives on the bottom floor. And we could call this positive 1/2. And we could call this guy negative 1/2. Okay? So every orbital is a duplex. We can put 2 electrons in there. They can't live in the same part of the house, but one can live up, one can live down. Positive 1/2, negative 1/2. Okay? So what does this spin magnetic tell us? It tells us where the electron resides and what are the possible values. It can be a positive 1/2 or it can be a negative 1/2. That's it. So let's bring this full circle. Let's go back to that address that I kind of arbitrarily wrote on this slide. And I'm going to write it up at the top here because I'm going to work where I have it written right now. All right. So where does this electron reside? If his address is 2, 1, 0, positive 1/2. So this first number 2 is the principal quantum number. So N equals 2. So this electron is in the second energy level. That's where he's at. The angular momentum quantum number is the number 1 in this case. So L equals 1. Possible values, so the options we had were 0 and 1. Well, for whatever reason, this electron chose to live in L equals 1. When L equals 1, what does that tell us about the shape of the orbital? What kind of orbital does he live in? Yeah, he lives in a p orbital. Okay, so let me click ahead here a couple of slides. So L equals 1. We know he lives in a p orbital. Okay, so he's in the second energy level. He lives in a p orbital, so he lives in a double-lobed house. The next number, 0, is the magnetic quantum number. So remember, the magnetic quantum number is positive L to negative L. So the possible values here are 1, 0, or -1. And remember, there was 3 different ways to orient that in space. So we could have the lobes up and down, we could have the lobes left and right, and then we could have the lobes kind of coming out at us, going back into the screen. So 3 different ways to orient that. So this guy's magnetic quantum number is 0. So he lives in the second energy level. He lives in a p orbital, and he chose, for whatever reason, he chose to live in the p orbital that's oriented left and right. So that's what the 0 means for us. He didn't want the up and down p. He didn't want the p that was coming straight at you. He wanted the left and right p. So that's what the 0 alludes to. And then the last quantum number, the spin magnetic quantum number. So he lives on the top floor of that duplex. So he's in the positive 1/2, and his neighbor is in the negative 1/2. So that's all that positive 1/2 means. Okay. So here's a table out of a textbook. I don't particularly love this table, but it works great for some students. So I do go ahead and include it in the slideshow. I'm going to do another video that will help you see some examples of how I might ask problems with quantum numbers. It's something that you're going to have to spend some time with, something you're going to have to maybe look at, come back to, look at, come back to until it fully sinks in. But please make sure that you take the time to work through these quantum numbers, because you're certainly going to see them again and again. Hope this helps.